In this video, we continue building on the foundation of random variables that were introduced in the previous video. So we just have a few more concepts that we need to discuss that are related to random variables. And so let's go ahead and do that now. So just as a reminder, without going back through all the definitions, we defined a random variable x and its PDF, right? And basically this will be for all x in the sample space. So this will be for all x in S, right? And we referred to this function as either the probability mass function or the probability density function, right? Now, there is another function that's closely related to this function that's associated with random variables. And this is how the function is defined and what it's called. So the cumulative distribution function or CDF is another function that gives the following probabilities. So that gives the following probabilities. So what other probabilities are there? Well, it's not that there are other probabilities, but just instead of asking the question, what is the probability that a random variable is equal to a number, the CDF asks the question, what is the probability that our random variable is less than or equal to a particular number, right? And this is the difference. So notice in the PDF, it is essentially, you could say it's exact, right? It gives you the probability that your random variable is exactly equal to a number. Here, it is not exact. It could be equal or it could be less than, and hence the cumulative. So everything, all the possibilities up to and including this possibility, the CDF returns that probability, right? So this is, I'll just say, this is cumulative. All right. So if you remember, in the previous video, we looked at two examples of experiments and how we define random variables that are associated with each of those experiments. I'm just going to use those two to show you, what the CDF looks like, right? And then we'll talk a little bit more about both, right? So what I will do is I will list the tables that we came up with, right? So the first one, if you recall, was that experiment where we had 5 men, 4 women, and we chose 3, and we defined the random variable x to represent the number of women that were chosen. And we went through, using our combination techniques, came up with this nice table. So here is the table again. And if you remember, the possibilities were 0, 1, 2, and 3. And we got that there was a 52% chance, no, not 52, 5 out of 42, sorry, chance that no women are chosen, a 10 out of 21 chance that one woman is chosen, a 5 out of 14 chance that exactly two are chosen, and then the probability that exactly 3 are chosen, that was 1 out of 21, right? So now let's see if we can write down the cumulative probability, right? And so let's see. So if we look at all the possible values again for our random variable and use these numbers here, let's figure out what the cumulative probabilities are going to look like. So let's start with x equals 0. So the probability, so if I plug my 0 in for my little x, it looks like this. And then, okay, well, what's the probability that x is less than or equal to 0? Well, x can't be negative, right? X can't be negative in this case. So in fact, let me break it up into the two disjoint pieces. So either x is less than 0 or it's equal to 0. Right? These are two mutually exclusive things. X can't be simultaneously less than 0 and also equal to 0. So I can use my axiom of probability and break this union because it's again, we are using the word or. It's less than or equal to, and we can split it into these two pieces. Well, this piece has a probability of 0 because the smallest x can be is 0. We can't have a negative number of women in this selection. So this is 0. And then the PDF tells me that this is 5 out of 42, right? So 5 out of 42. Oh, let's fix that. So 5 out of 42 is the probability that x is less than or equal to 0, right? Well, let's see what happens when x is equal to 1, right? Little x. So what is the probability that the number of women that we observe in this committee is less than or equal to 1? Well, we can do a similar type thing here. We can break it up and say, well, it's the probability that x is less than 0 plus the probability that x is equal to 0 plus the probability that x is equal to 1. Because again, these are all mutually exclusive. None of these three things in parentheses can occur simultaneously. So because they're all disjoint, again, the axiom of probability tells me that I can split these into separate terms and add the probabilities together. And it's kind of getting, a little tired for us to write this when we know it's not even a possibility. So maybe the next go around we don't even have to write this because we know that's going to be 0. And then let's look at the values of x that are actually possible. So the probability that x is equal to 0, that's the 5 out of 42, and then plus the probability that x is equal to 1, that's 10 out of 21. And now let's write both of these with a denominator of 42. So that will be 20 out of 42 plus 5 out of 42. So that's 25 out of 42. So if you notice what we're doing as we go in this process, it's like we are accumulating, we're adding up all the possible probabilities up to and including this number, right? And again, it might seem like a strange thing to do, but you'll come to see how useful the CDF is. In fact, both of these functions are equally useful, PDFs and CDFs. All right? Let's continue because we have to do this for all the possible values in our sample space. So we have 2 completed, we have 2 more to go. So now let's look at what happens when x is equal to 2. So the probability that your random variable is less than or equal to 2, well, the practical possibilities are that x is equal to 0 or 1 or 2. Right? And again, we can add these all together in this cumulative way. So we're now adding this probability plus this probability plus this probability. Right? And then, so we have So let's see, we have our 5. So all of these are best written with the denominator of 42. That will make the addition um, possible or easy. So then we have our 20 out of 42, and then 15 out of 42. So what do we have here? So we have 40 out of 42, right? Or we can write that as, well, let's see, what's that? We can divide by 4. No, surely there's more there. Well, yeah, because that would be, yeah. So that's 10 out of. No, we can't divide that by 4. What am I thinking? So 20 out of 21. Right. So again, there we are accumulating all these probabilities, and now we get to the last possible value of x, which is 3. So when x is equal to 3, the cumulative probability function or distribution function gives us this value. So it's the probability that x is equal to 0 or 1 or 2 or 3. Now think about this. We know that this sample space consists of exactly 4 values. And we're now going to add up the probabilities of those 4 values. Well, think of what the first axiom of probability. It says that the probability of your sample space is equal to 1. So if we're now going to add up these 4 probabilities, the only 4 possibilities, right, that could occur from this experiment, we must get a value of 1. And we can see it because look, we added up the first 3, and that gave us 20 out of 21. And look at what we have left to add, 1 out of 21. So adding these 4 together now, so there are lots of ways you can reason through it, but we've now accumulated all the possible probabilities. And this is another check to make sure that your PDF is correct. Because if these probabilities add up to something that's less than 1 or greater than 1, then we violated our first axiom, right? So now let's state both of these together, right? So I'm going to state the PDF on this side. I'm going to restate that table. So the probability that x is equal to little x. And we have these, again, these are exact probabilities. That's why we're using equal to. And we got 5 out of 42, 10 out of 21, and I apologize if, tonight you're going to dream about these numbers because we're seeing them so many times, but you could dream about a lot worse things than numbers. And here's a CDF. Again, we can also put it in the form of a table. All we would have to do is just to make sure that we change that equal sign to a less than or equal to. So like this. And then list the values that we just had. So let me go up just a little bit so you can see the first value, the 5 out of 42. So again, it will list all the possible values. Yeah, we don't need the 5 over 42 because it's going to be the same as this one. And then 1, 2, and 3. Right, so it starts out at the same value, 5 over 42, but then the probability that x is less than or equal to 1, so then you add these two together, and that's how we got the 25 out of 42. And then the probability that x is less than or equal to 2, that's when we add these 3 together, and we got the 20 over 21. And then when we accumulate all the possible probabilities right here in our table, they add up to 1, right? So that's the CDF of your random variable. Now, so we've used the table several times as a way of conveying what this PDF represents. But when you think about functions, and in your study of functions going all the way back to algebra, a lot of it involved things that were graphical, right? And it turns out there are graphs that are associated with these two functions, right? The PDF essentially has two graphical representations. The CDF has one, right? So let's look at some graphs that are associated with the PDF. Like, what if I wanted to put this information in a graphical way? Well, what you do, and this is why switching to numbers is so helpful, because we have lots of ways. Like I said, there are lots of things we can do with numbers, and this is one of them. So one way to represent the PDF is to, on your number line, on your horizontal axis, indicate the possible values, right? Well, so we have 0 there, we have 1, we have 2, we have 3. You could even, list more values, but our graph is really just going to be associated with the values x equals 0, x equals 1, x equals 2, x equals 3, right? So that's my x. Now, you could put this label on your vertical axis, but it looks a little clumsy. When you think of how we usually label the vertical axis, we either use y, right, or we use like f of x. So it is actually fairly common for us to represent the PDF using a lowercase f, right? And then that way I could say, well, you know what? Yeah, let me get rid of this thing and have it labeled the way we typically label our vertical axis, right? So little f of x is a very commonly used notation for the PDF. And then, well, how do we graph this? It's, there's no equation, there's no like x squared or sine, or how do we graph something like this? Well, one way to do it is essentially to have your probabilities be reflected on the vertical axis. And so let me see, probably the best, looking at these numbers, if you convert them to decimals, this one is approximately 0.12. This one is approximately 0.48. This one is approximately 0.35. And then the 1 over 21 is approximately 0.05. So if I put a scale that kind of reflects these, so maybe if I go up by 2's, that seems reasonable. So like 0.2 and then 0.4, and then I don't need to go beyond 0.6, but you can go up to 0.8 if you want. And then what you do is you're going to draw a vertical line, or line segment, I should say, that's directly above each possible value of x, and the height of the line is determined by the probability. So for instance, this one is going to start from 0, and it's going to go up just a little beyond halfway to 0.2. So maybe like that, right? And you put a little, it's just a vertical line segment, right? That starts along the x-axis, right at each possible value of x, and the height of the line segment, it reflects the probability. So let's look at this one. So starting at 1, I have to go up to roughly 0.48. So that's a little less than halfway there. But again, this is just a sketch. and then you have just that little line right there, right? And then above 2, we have to go to 0.35, so probably about 3/4 of the way there. So there we go. And then the last possible value of x, really low probability. So the low probabilities will have a very short vertical line segment. So 0.05 is a quarter of the way here. So basically a half of this one. So again, it's very, very short, basically something like that, right? And this is called a probability line chart, right? And it's useful for these discrete random variables, right? So this is called a probability line chart. And that's what it is. It's a bunch of lines, right? Or line segments to be precise. And the height reflects the associated probability for each possible value of x, right? So that's one way that we can represent the PDF. Another way is where we can do what's called a probability histogram. What does that look like? Right? So the setup is going to be very similar. Again, you're going to have things going up a certain height, and that height will reflect the probabilities. But this is how it works when another measure. So I'll use the same scale that I did there, the 0.2, the 0.4, and I'll just go to 0.6 like that, right? And let me mark off the other possible values of x. All right, so what are we going to do with these? Well, instead of having just a line segment, we're going to have rectangles. And the rectangles are going to be centered, right, at each possible value of x. So it's like it's going to straddle each, so you're going to have half of the rectangle on this side and the other half on this side. And you do that for each value of x. And then the height of the rectangle, again, goes up to the probability associated with each x. So it's basically now take this line, give it some width, and cover this. So this is what it would look like for this particular case, right? So again, it's not going to be super precise, right? But it's going to look something like this, and then you can even shade the rectangle. And then for the 1, it's going to go up basically there, and then cover it, and then come down, and then we have that. Yeah, just again repeat this process for each possible value of x, and then for the 0.4, so again it goes up roughly about there, and again it covers this interval. And if you notice, the width of each rectangle is 1. Right? The width of each rectangle here is 1. The height is the probability. So actually the area of each rectangle that I'm drawing here is the exact probability in the PDF, right? And here's the last one. Now this is a very short rectangle. So basically like that, and there we go, right? So so this is called a probability histogram. And you might wonder, like, why do we have two? Well, they're both simple graphs, but the thing I like about the probability histogram is what I just said, that the area of this rectangle is exactly the probability that my random variable is equal to 2, right? So the area of let's put it this way, the probability of each um, value of x is equal to the area of its rectangle, its corresponding rectangle is equal to the area of its rectangle. Pretty cool, right? Pretty cool in the sense that we can use area to find probabilities, or we can use area to represent probabilities. That's going to be a key thing when we move to the continuous random variables. So keep that concept in mind. Okay, so those are two graphs that are associated with the PDF. What about Mr. CDF? Well, first let's address the notation, right? So I'm saying that we will often use the lowercase f, right, to represent the PDF. Well, we would like something comparable to represent the CDF. And since it's the same random variable, we don't really want to use a different letter. We want it to be the same letter, but what we can do to represent or to reflect the cumulative nature of the CDF is to use a big f of x, right? Now, just as a little teaser, thinking back to calculus, do you remember like our fundamental theorem of calculus where you're trying to like integrate a function f of x, little f of x, and you end up using big f of x to represent the antiderivative? Well, there's a reason why we are choosing little f here and big F here. So again, a little teaser for the calculus to come. Okay, so in terms of graphing the CDF, actually, before I do that, let me show you how we can represent this information in the table as a piecewise function, right? So it can look like this. Should I do the piecewise? Yeah, let's do that. So f of x, so now our CDF, it can take on, so whenever your x value is less than 0, so whenever it's negative, we know that there is no probability associated with that because we can't have a negative number of women. So I'm going to just describe it like this. So this function is going to be 0 whenever x is strictly less than 0. Whenever x is between 0 and 1, including 0 but not including 1, it means that we've only accumulated 5 over 42 as our probability. So it's going to be 5 over 42, and that is whenever x is greater than or equal to 0 but strictly less than less than 1, right? So we haven't quite gotten to 1 yet. Once we get to 1, but before we get to 2, it's going to return this value. So it's going to accumulate the probability associated with 0 and with 1 for a total of 25 out of 42. But that only occurs whenever x is between 1 and 2, including 1 but not including 2. And then once we get to 2, but before we get to 3, it will have accumulated 20 out of 21, right? So 20 out of 21. Then once you hit 3, you've accumulated all the possible probability, and what we can say is when your x is greater than or equal to 3, then the probability is always 1. So you've reached that maximum probability, and we've accumulated everything that we can. So this is it is a piecewise function. It's not typically the piecewise function that you would see in calculus, but it is a discrete version of that, right? And this form of and this gives us the exact same information in the table, but it's easier to sketch if it's in this particular form. All right, so let's see. Maybe what I'll do is move over here. And actually, let's go down as well. Okay, so now let's see if we can sketch this CDF. So what am I going to do? Well, so we can see that the values are going to range from 0 to 1, right? So like this. And then it's just a matter, based on these probabilities, it's, it may be something like, let's see, if we do it in terms of 42s, so like 10 42s, 20 42s, and so forth. So let's do something like this and show you what this graph looks like. And let me put our x values there. All right. So I'm going to sketch this one in green, and basically what's going to happen is, so the graph of the function is going to be equal to 0 because there's a 0 chance that our x values are negative. So the graph will be 0 right until you get to x equals 0, and at x equals 0 you're going to have a jump, and it's going to jump up to 5 over 42. So let's just say this is 5 over 42, right? So it jumps up there, and then it's going to take on that value until, again, this is a constant value, until you get to 1. At 1, you'll have another jump. So that circle will be open, but then when it jumps up, then the next one will be filled in. So basically 5 times that. So 1, 2, 3, 4, 5. So basically, let's say about this height, right? And then it's going to stay that value until you get to 2, and then it's going to have another jump, right? And it's going to jump up to just before you get to 1, so basically here. And then it's going to be constant for those values of x, and then at 3 you have another jump discontinuity, and then it jumps up to 1, and then it stays that way forever, right? So you start out with a 0 probability, and then every time you hit a possible value of x, you accumulate just a little bit more area. And now, not area I should say, but you accumulate a little bit more probability. And now each jump represents the likelihood of that specific value of x. So this was the jump of 5 over 42. This right here, this jump is our 10 over 21 because we accumulated that to get to this height, right? And then this jump right here is our 5 over 14. And then finally, this jump here is the 1 over 21, right? Let's actually label that if we can. So yeah, because they're kind of small. But that jump there is the probability that x is equal to 0. So that's the probability that x is equal to 0. This jump here is the probability that x is equal to 1. This jump here is the probability that x is equal to 2. And then finally, that little tiny jump there, that one, is the probability that x is equal to 3. Right? So the information is there. It's a little harder to see it on the graph of the CDF, but it's there. It's the magnitude of the jump, those finite jumps that occur every time you hit another possible value of x. That causes your probability to be accumulated. And then you can't go beyond 1 and that's why once you hit this total probability, it stays, because there are no other possible values of x that would cause it to jump even higher, right? So they always start out at 0 and accumulate until you get to 1, right? So there are a few more properties and ideas related to the PDF and the CDF that we're going to discuss in the next video. So please tune in, and I look forward to seeing you. See you then.